a better market than
Okay, thanks everybody for coming. And then we have today Professor Nazarewicz with us, and it's a very honor to introduce him. He got his PhD in nuclear physics at the University of Warsaw, and currently he's a professor at the University of Warsaw and also a distinguished professor at Michigan State. He's the John A. Hanna Distinguished Professor in Physics. He's also the chief scientist for the FRIB project, which is the flagship experiment in low-energy nuclear physics in the United States. And he has been also for many years professor at the University of Tennessee, and he has been a fellow of the physics division, corporate fellow at the Oak Ridge National Lab, and he has held different visiting professorship in different places in the UK, in France, in Japan, in Poland, in Sweden, Germany, and other countries. He has supervised about 10 PhD students and about 10 master's students. He's a member of different associations, and he's been in panels and review committees in different places in the United States and abroad. He's fellow of the Polish Physical Society, the European Physical Society, fellow of the APS, of the IOP, and of the AAAS as well. In 2012, he got the Tom Bonner Prize of the American Physical Society for his work on theoretical nuclear physics, which is a very distinguished award. And he has published 5 books and volumes, about 10 review papers, more than 350 scientific publications, and all his work has been cited almost 20,000 times, which is one of the most cited nuclear physicists in the country. He has more than 200 invitations for conference and almost 300 invited seminars and colloquium. And today is the first time that he comes to Kansas. So, and we're very pleased to have him here. And he will discuss about his work on theoretical nuclear physics.
So thank you very much, Dan. It's very embarrassing to hear all these nice things. You know, so I am to translate this all introduction, I am a nuclear theorist and I compute nuclei, okay? Thank you very much. So thank you very much for inviting me here. It's been a great day. I had wonderful discussion and I learned about university and campus. Great visit, okay? So the plan for this presentation is to tell you about the recent progress or general situation in low-energy nuclear physics, where we are, and the nuclear landscape, that is the territory where nuclei live and die, will be the motive of this talk. So I decided to take this quotation from the recent National Academy Decadal Study Report on Nuclear Physics, which nicely emphasizes the role of the nucleus in the universe. So we are all made of nuclei, this lecture room and our bodies and everything around in the visible universe. So I'm not going to discuss the difference between visible and universe, because this number would not be so impressive, okay, as you know, okay. So this is the diagram, which, by the way, can you hear me over there? Super. And also, if you would like to interrupt me, okay, at any time, do not hesitate. I'm very happy to be interrupted. Okay, so this shows the general structure of the field. Okay, we have several islands of activity here. This is the island of quark-gluon plasma, and this is the island of hadrons, like protons and neutrons and pions, and then light nuclei, heavy nuclei, and stars. And those islands are connected by bridges, and each bridge is a challenge, right? So the first bridge represents the problem of confinement, and how do we go from early universe, which was dominated by quark-gluon soup, to hadrons, and then how to build nuclei, light nuclei, out of elementary hadrons. okay, and heavy nuclei using effective interactions. And then these are stars. So there's a lot of nuclear physics in the cosmos, and we would like to find the connection between, say, neutron stars, supernova, etc., and nuclear physics. So as we go in this direction, distance increases, and this arrow represents resolution. Okay, so resolution, so energy of our probe must get larger if we want to probe physics here, and this gives us insight into most fundamental building blocks. Okay, so what I would like to do today, I would like to ask why, what, how, and where, and more specifically, I would like to say why should we care? What are the overarching questions, how to answer those questions, and when we are today. So this will be a little status of the field as of 2016 March. Okay, so in my other life, I collect antique maps. And there's actually a great connection between theoretical nuclear physics and map collecting, okay? So this one, so I try to select some relevant maps which are relevant for this meeting. So this is one of the first map of the Americas by Sebastian Münster from Basel, okay, from 1544. As you can see, general structure is already there. And we have Florida and this Francisca, which is today's Canada, okay? And this is where Kansas is, somewhere here, yeah? Yeah. Well, it was not very well known to the European map makers at that point, okay? And then the map of Joliot-Ottens, 1756. You see more details, of course. Now, this part, it was called Florida. It was not even called Louisiana, right? Florida. And then Canada was not that far, right? California, as you can see, is still represented by an island. Okay, so people thought that California was an island then. Okay, and this is one of the first maps of Kansas territory. Okay, which includes Kansas territory. De Silver, 1856. This was a wonderful time. You had only 1 hour, you know, to St. Louis to see one NFL team. And there were Broncos were in Kansas, okay? So you had your own team at that point, okay? And then, of course, this was corrected. So Kansas was admitted to the Union. Colton, 1878, characteristic rectangular structure, except for this little part where you are here, okay? But we don't have to do it in this way. We can just take a picture of Kansas from the sky, and this is the satellite image of Kansas, except, of course, for county lines, which you don't see from satellite. This is common for students, okay? And then it's just precise, you know, what you see, what you get, okay? So this is very similar in nuclear theory. We started from very phenomenological, very rough models, which give us some broad brush ideas about the nucleus, and today, I may say, we are approaching this level of precision. Okay? So nuclear experimentation provides unique data, and nuclear models are providing very quantitative understanding. Okay, so the general introduction. So this is the quantum ladder, which puts various physical systems in the energy scale. So complexity goes in this direction. So we are going from high energy physics to nuclear physics, AMO physics, condensed matter physics, and astronomy, okay? Reduction goes in this direction. We are reducing complex system to simple ingredients, and complexity or emergence goes in this direction. This is subatomic, atomic, macroscopic, okay? So as you can see, nucleus plays a very special role in this in this plot, because nucleus is really on the interface between reduction and emergence. Okay, so in the same nucleus, you might look for phenomena and features which are typical to high energy physics, and you can test a standard model or some aspects of it. And in the same nucleus, you can look for collective effects, emergent phenomena, which are typical for condensed matter physics, atomic physics, phenomena such as superconductivity or phase transitions. Okay? So atomic nucleus is very special in this point of view. Okay? So this is the territory, the nuclear landscape, and the territory was basically inhabited long time ago. So the time scale we are interested in, it is between this time scale from QCD transition, where color singlets were formed, and this was around 10 milliseconds after Big Bang till today. So this physics spans 13.8 billion years. And the distance scale is between 10 to the minus 15 meters, or femtometer scale. This is the radius of the proton, to around 12 kilometers, which is the radius of a neutron star. Okay, so this is the time scale and distance scale, and the questions which the field collectively answers is here. Where do nuclei and elements come from? So what is the origin of nuclei? What is the origin of elements? And how are nuclei made and organized? Okay? What are practical and scientific uses of nuclei? And there is this decadal study report which very nicely elaborates on all those questions, so I strongly recommend it. Okay, so this is a more precise picture of the nuclear landscape. So this is the nuclear territory, and neutron number goes in this direction, proton number here, and each square in this diagram is an isotope. It's a nucleus. Okay, the nuclear landscape ranges between the drip lines. So this is the neutron drip line. This is the proton drip line. There are no nuclei existing beyond drip lines, because as you will go, if you fix, for instance, the atomic number, say 10 isotopes is equal to 50, and if you will go in this direction, at some point the nuclear chemical potential will become 0, and at this point the nucleus will become unstable to neutron emission. And this is what determines the limits of nuclear existence. The separation energy becomes 0. So here we can place the sign caution no binding. There's no matter, nuclear matter, beyond the neutron drip line. There's no stable nuclear matter beyond the proton drip line. And there is another interesting limit which we do not fully understand. So this is this northeast corner, very wild territory of super heavy nuclei, and we really do not know how far can we go in this direction. Yeah, well, if you are very precise, you would say, well, there is some life actually outside the neutron drip line, because if you go to the neutron number of the order of 10 to the 57, then there will be a neutron star, of course, right, which has a mass of 1.4 solar masses, 12-kilometer radius, and of course it's made of nuclear matter, but then you need this little gravity to keep it together, right? But we are still very interested. So neutron stars are usually considered as a part of the grand nuclear landscape. Okay? You can see here those drip lines. You can ask, how do we know those drip lines? Experimental data are shown here. The stable isotopes are marked by black squares. And those which were approached in the laboratory are marked by these green squares. Okay? So you see that in this region, we are very, very far from where the data are known. Okay? So I have a quiz for students at this point. So what do you think? How many stable isotopes, that is non-radioactive species, exist in nature? At least in our universe. So what is the number? Give me the order of magnitude. Nuclear physics students. Well, no, they are silent. Just give me a number, whatever. 100. All right. This gentleman gave the right order of magnitude. It's 288. So this is not bad. So if you count those are only even ones. If you add odd ones, it will be 288. And you have around 3,000 which were found. And how many protons and neutrons can be bound in a nucleus with the up to 120 here? Well, the answer is around 7,000, okay? So the territory, current nuclear territory, is around 7,000 isotopes, okay, which have very different properties. And this pink area here marks the theoretical uncertainties. Yes, sir?
So why doesn't then your pink neutron drip line go to nearly 7,000 then? So you're saying that if I have
7,000, yes.
I have one nucleus with z equals 120. That's your y-axis. Shouldn't the pink line then be?
No, in a nucleus with z up to 120.
Oh, so it's all the
up to. So what is basically the range of this landscape? Up to 120, okay? And the pink line actually shows the theoretical uncertainty. So if we take our best models of nuclear structure and try to extrapolate, and you can see how massive this extrapolation is here, okay, we get this theoretical uncertainty. So this is...
How come there's none of those things around?
Excuse me?
My impression, and I think what you said it, is that the experimentally known ones are in the green and black, and all this white stuff is...
Is terra incognita.
Yeah.
Yes.
Okay, but where are they? Why don't you find them in quark searches and other searches for rare?
Well, I mean, you can... This is, so the question is, where are those guys in the white area, okay?
Yeah.
They're all radioactive, of course. You know, so stable isotopes are only the black lines. So even if you produce
stable under strong interactions.
Stable under
unstable under weak interactions.
Yes. So the guys which are black are stable total. They are stable with respect to strong force and electroweak force. Okay, they just don't, they are not radioactive. If you put a black square nucleus in a bottle, it will stay there forever. Okay, but radioactive nuclei, they have lifetimes. Those which are on this side, they will beta minus decay. Those which are on this side, they will beta plus decay. And even if we produce them experimentally, we have to keep them for a long time to see them, of course. So yes, so we believe that those are, those exist in nature. Most of those white nuclei here will beta minus decay. So their lifetimes are totally governed by weak force. Okay.
Where are the super heavies, the stable super heavies that have been talked about?
Let me talk about it later.
Okay.
This is going to be covered. Okay. So let me show you a few challenges now. Okay. So the interesting question is the origin of the elements, and this upper diagram shows basically chemical evolution. So just after the Big Bang, very few elements were created, and so Big Bang nucleosynthesis. In the older stars, elements up to mass 100 were created. So these are basically the abundances. The heavy elements heavier than iron, most of them were created in the rapid neutron capture process, okay, which is shown here. So this is the only contribution from our process to solar abundances, and this is what we see experimentally. So when you look at the amount of stuff in our solar system, okay? So now you would like to disentangle, you would like to understand which element came from what process. And our process is of particular interest because we know already a lot about it. We still do not know where the site of our process is. Okay? So we do not know whether these very high neutron densities, which are needed for captures, were created in supernova or in neutron star and black hole, neutron star or neutron star black hole mergers. So those are two contenders for the site of the R process. Okay? So as I said, is that half of neutron-rich atomic nuclei heavier than iron, nickel, were built by neutron-driven R process. So we know that the gold in your jewelry comes from our process. We know that the lead in your battery comes from our process, undoubtedly. We know that plutonium-238, which powers Curiosity Mars rover, comes from our process, and elements of magnets in your hybrid car. Dysprosium, right, comes from our process. But whether it is from merging neutron stars or supernova, we still don't know. So there's a lot of actually research which tries to address this question. Okay? So how are nuclei made? And it is, at this point, it's useful to show this plot of degrees of freedom. So on the most fundamental level, we deal with quarks and gluons. Those are the fundamental building blocks of QCD. As you go higher in energy and lower in resolution, then we can talk about constituent quarks, and then baryons and mesons, and then protons and neutrons. And even at lower energies, we can replace protons and neutrons with proton and neutrons densities and currents. Okay? And the right-hand side shows basically the area of research: hot and dense quark-gluon matter, hadron structure. This is nuclear structure reactions, the search for new standard model and applications of nuclear science. Okay? So this field is rooted in QCD. Okay? Nuclear structure. All atomic nuclei exist because of strong interactions. Okay? And so we are living in times in we are slowly learning about the origin of nuclear force and how are the lightest nuclei made starting from QCD. Okay? So this shows some papers, relatively recent, in which nuclear interaction was derived, or some aspects of it, from lattice calculations. And you can see a familiar figure which shows very small binding, and then this repulsive core, which represents Pauli principle between quarks. This diagram shows the actual calculations for finite nuclei. Those are the magnetic moments of the lightest systems with mass less than 4. So you can see helium-3 and helium and tritium. So those magnetic moments were calculated on lattice. Okay, this is a 9-body quark problem on lattice. Okay, but I think that the triumph of lattice QCD when applied to nuclear physics is this recent work by BMW collaboration in Europe. Okay, so we know that neutron is slightly heavier than proton. So this is the neutron mass in MeV, 939.56. It's very well known. Proton mass is very light, and this is electron mass here. Okay, so you see that if you add the mass of electron and proton, this is still below the mass of the neutron. Okay, so this is significant. And the mass, the difference between neutron and proton is a very small number. Okay, so what is the origin of this imbalance? Okay, so in this recent paper in Science from 2015, this lattice collaboration from Germany and Hungary did state-of-the-art calculations in which they took completely into account the dynamics of gluons. So those are unquenched QCD calculations and also unquenched QED calculations. So strong interactions and electrodynamics were completely correctly taken into account. and here you have the prediction, okay? So the experimental difference, this difference between masses is 1.29 MeV. In those calculations, the mass splitting was predicted to 1.51 with the error bar, which is consistent with this. And the mass, if you just consider strong force, the QCD mass would be mass difference would be 252 MeV, but QED, that is electromagnetic force, gives you -1 MeV reduction. So what we see in nature is a subtle cancellation between QCD and QED. Very interesting. One could, of course, talk about this paper much longer. They made other predictions, not only for nucleon, but also for other systems. And you can see here very nice agreement with the data. Those are parameter-free calculations, only standard model, of course.
Do the lattice calculations handle the spin as well?
Yes. Yes.
Does this give an upper limit on the fine structure constant for a stable universe?
Yes. It is all in the paper. Actually, alpha QED is not fine-tuned. There's actually a broad range of possible values, which would be allowed.
Close to 1.
Well, no. I mean, there's a figure in the paper which shows it, okay? So I strongly recommend this work, okay? So let me go to nuclear physics of heavier nuclei. So this is the standard picture of the nucleus. Well, this is a standard picture of the atom as formulated by Niels Bohr. So electrons move in atoms in shells. Shells are separated by gaps. Gaps correspond to noble gases, particular stability of systems which have those numbers. So the analogon of this picture in nuclear physics is the model of nucleonic shells. Protons and neutrons move in shells. They move in some kind of average self-consistent potential. They bunch in shells, and shells are separated by energy gaps, and those gaps correspond to magic numbers. So this is the picture of the nucleus, which you can read in any textbook. Okay? So it's a familiar picture. Okay? Well, we've learned over the last 10, 15 years that this picture is very incomplete, that this picture of shells and gaps breaks down as we go closer to the drip line. Okay? If you look, for instance, in this plot for energies of the lowest 2+ states in nuclei, you would expect the energy of the lowest excitation to be very large if you have a doubly magic nucleus or a magic nucleus, because the nucleon has to go across the gap. Okay? We see that indeed, for instance, in these calcium isotopes, calcium with 20 neutrons has this very high lying 2+ state, and calcium with 28 neutrons has also elevated 2+ state, consistent with our knowledge about shell model. But then you go to calcium with 32 neutrons, 34 neutrons, and you can see those high excitations. So, and there are similar pathologies here, which I do not have time to discuss. So there is now an ample experimental evidence that the familiar pictures of shells, okay, in orbits breaks down if we go to nuclei which are more neutron rich. Okay. This is actually a very interesting recent result from MSU, which shows that oxygen-26 primarily decays to oxygen-24 by emitting a correlated pair of neutrons. So the data are shown here. So this is this cross-section for oxygen-26 to this. And you can see there's this very low energy peak, around 100 keV. And if you estimate the lifetime for this decay, you will see that this corresponds to as long as picoseconds. When at the time scale of picoseconds, we can talk about radioactivity. So oxygen-26 is perhaps the first nucleus which exhibits a dineutron decay. A dineutron is significant because protons and neutrons in atomic nuclei are paired in Cooper pairs, very much like in superconductor. So what you see here is basically a decay or emission of correlated neutron pair from unstable nucleus. The binding energy, the separation energy is extremely small, so the lifetime is longer. Okay, so let me show you where the frontier of theory is. And this is a representative example. I know that James Vary was here several weeks ago, and he showed you many excellent examples. But let me show you an example from some recent work. So this sequence of Feynman diagrams shows the nuclear force. So this is the nucleon part of the interaction. So those are only two-body forces. In the lowest order of the chiral perturbation theory, you have only those two graphs. But when as you go higher, you will see more graphs. So this dashed line indicates a pion, a dot indicates a contact term. Short range, unknown behavior, which is represented by coupling constants. And we see that at 2LO level, three-body forces enter the game. So three-body forces are important in nuclei, okay? So as you can see, it's fairly recent business. This N2LO interaction, which was derived in 2000, 2002, was optimized simultaneously only last year, or 2 years ago. So how this optimization was carried out? Well, to scattering experiments, to phase shifts, to 2 and 3 body systems, to alpha particle, and to radii and masses of some oxygen isotopes. So in this paper, this interaction was used to make predictions for calcium isotopes. And those are ab initio calculations. So this is the solution of 40 or 48 body problem with this interaction. No approximations are made. So this is the exact solution of 48 body problem in the case of calcium-48. And now you have a comparison between charge densities of calcium-40, 48, and experimental data from electron scattering. And this is actually the difference between the data for calcium-48 and 40. And you can admire actually the good agreement with experiment. So it's totally within experimental error bars. And those are the predictions for the weak interaction form factor in calcium-48, which will be probed by the parity violating electron scattering experiment at Jefferson Lab in the CIREX. So nice Nature paper from 2016. Okay, so now coming to your questions. You know, what are the limits of atom and nuclei, and do super heavy elements exist in nature? Okay, this question has been with us for a long time. Okay, early calculations in the 60s predicted the island of super heavy nuclei, which were expected to be very stable, okay, or stable or very long-lived, like days or months or years, okay? And some people got so excited that even started thinking about possible defense applications, okay? Well, the reality is shown here. So this is where we are today, okay? So around 30 new super heavy elements were found since 2007, okay? So 2 of them were confirmed in 2012. So fluorovium and livermorium were named several years ago. So this year, elements 117, 115, 113 were confirmed, and they will be named soon, okay? Lots of wonderful data were obtained for elements above 102, and chemistry was carried out for elements 106, 112, and 114. And this is very exciting, because in those elements, the product of atomic number and fine structure constant is getting dangerously close to 1. It's still safely away from 1, but the heaviest is 118, okay? But it's a big number, okay? It's not that extremely different from 1. So relativistic effects okay, are absolutely crucial. So quantum chemistry is really a wild, wild west here, okay? So now, answering your question about where are those long-lived elements. So theory predicts the island of longer-lived elements around neutron number 184. So it is here. So this holy grail is where we hope these longer-lived superheavies are, okay? And this shows the systematics of alpha decay half-lives for various elements, for various isotopes, as a function of neutron number. And we are around 175 or so. Those lifetimes are going up. And this is logarithmic scale. So if you have fantasy and guts, you can, of course, extrapolate this to neutron number 184, and you can extract possible lifetimes, okay? So this is where we are today. It will be extremely difficult to get us from here to here because of the lack of beams and targets, which can produce a compound nucleus, which will have those characteristics, okay? Okay, so this is the current Mendeleev table, okay? So all those elements were either named or confirmed, and the confirmation will be done this year, okay? So the UPAC announcement was properly done on December 30th, you know, in which they officially stated that now those laboratories, Japanese, 2 US labs, and Dubna have rights to name new elements. So this will happen within 2-3 months. So check the news. Japan will get their first new element, okay, perhaps Japanium, JP, most likely, okay. This was tour of force, of the force experiment. They were looking for element 113. They were trying to synthesize it using so-called cold fusion reaction, which has nothing to do with other cold fusion, okay. This is good cold fusion. And they, the cross-section for this production synthesis was so small, they saw 2 events per year. Well, they could run the accelerator for 3 years. So they saw several events. And this has been now confirmed. Okay. Well, I have no time now to discuss the structure of topologies, exotic topologies in superheavies. If somebody is interested, I can talk about the voids and cavities. Another challenge, actually, in the field is the quest for understanding the neutron-rich matter on Earth and cosmos. So what is the behavior of neutron matter, neutron-rich matter, which is, for instance, in neutron star crust? So as you will travel from the surface of neutron star deeper and deeper towards the center, you will see fantastic crystal-like structures. So these are some predicted phases of nuclear matter in the crust, which corresponds to relatively low density. So those fantasy shapes got names such as pasta shapes like lasagna, spaghetti, etc. Okay? And then as you go deeper, you see that there are more that there are more nuclear matters and cavities. There are also cavities here, and these phases are called antipasta. Okay? And this is all expected by theoretical models today. Okay? So this is actually quite fascinating area of research. If you have a good nuclear model, which does well on nuclei, you can try to use this model in TOV equations, which gives you the structure of neutron star, and then you can make a correlation plot which correlates the radius of lead-208, which is several femtometers, with the radius of neutron star, and you can see that those two quantities are very well correlated. So by measuring carefully the neutron radius of the neutron distribution in lead-208, you can get some important physics insights about the equation of state of nuclear matter, you know, which determines the structure of the neutron star. Okay? So this is truly...
Does it imply then that the density doesn't saturate in neutron star?
the density changes
It changes,
from,
right? So
from the surface all the way to the core, and it can be like 5 times saturation density because of the pressure, of course. Yes. So equation of state gives you the dependence, right, of energy on density. So in order to understand this, one needs astronomical observations. Now we got the first announcement about gravitational waves. Gravitational wave astronomy will be extremely useful to get some ideas about the transport of neutrinos, for instance, in neutron star class. And FRIB appears for the first time now. This is the machine which will tell us a lot about properties of very neutron-rich systems. And before I tell you about perspectives, let me mention one more thing, that atomic nuclei are wonderful laboratories of fundamental symmetries. And this is one example. If you look at the structure of the nucleus radium-225, it has this kind of shape, pear-like shape in the intrinsic system. And in such a nucleus, which looks like a pear, there is a chance to enhance the electric dipole moment. The measurement of the non-zero electric dipole moment would tell us the degree of CP, what is the degree of CP violation in the universe. And CP violation is equivalent to time reversal violation, and this can tell us about why do we have a dramatic excess of matter over antimatter in our universe. So by measuring some properties of radium-225 and looking for electric dipole moment, we can put some stringent constraints on something very fundamental. So right now, there's been actually a paper from Argonne in 2015 by Baker et al. They managed to trap radium-225 and provide some upper estimate for the EDM, electric dipole moment. So very nice work.
What's the spin of this nucleus?
Spin 3.5.
So you got a lot of moments.
Excuse me?
They talked about, you talk about the other moments?
Oh, there are various moments, actually. So the measurement here is that of the shift moment. We want to measure shift moment.
Yeah. That's what they always talk about with
Yeah.
the neutron.
Yeah.
But you have a lot more moments with spin 3.
Yeah.
So do people talk about measuring those for
I don't
CP violation?
I don't think so. I'm sorry. It is probably 1/2 minus. It's probably 1/2 minus. So other moments are not present. But there are other cases like radon, which have larger moments like 7/2 minus, which are also octupole candidates. And
See, I can't be sure whether it can have a pear shape with spin 3. You can't with spin 1/2 because you don't have enough degrees of freedom.
no, this is the shape which is in the intrinsic system, in the body, is body fixed frame.
Yeah, but that's why I asked about the spin.
Yes. No, it has non-zero spin. I'm just saying that in radon is 7/2. Okay, in radium-225 is probably 3/2, but maybe it's 1/2. I don't just remember now. Okay, so quickly, I still have a few minutes to discuss prospects, okay? And experimentally, those are various facilities in which rare isotopes are produced. Okay? And so now we got fantastic results from the first generation of facilities, such as NSCL at MSU, or Holyfield facility at Oak Ridge National Laboratory, and smaller facilities like Argonne. In Europe, GSI in Darmstadt, and Isolde in CERN. Many of you probably know Isolde from your trips to CERN. And in Japan, RIKEN facility in Wakosi. Okay, this gives you the flavor of where we are now and some projected facilities. So every facility at MSU will be the largest one in 2001. So a few words about FRIB project. So this is the next largest investment by Department of Energy, Office of Nuclear Physics, after 12 GeV upgrade of Jefferson facility. Okay, So this would be the price tag has been shared by Department of Energy and the state of Michigan and Michigan State University. This facility is being built on campus, okay? Is between medical school and law school and NSCL and the Institute of Veterinary Medicine. So it is literally in the campus, in the center of, in the corner of campus area, okay? And this is where we are almost now. So the basic civil engineering has been finished, and people are starting putting magnets, superconducting magnets. So this is the layout of the facility. Okay, so the heart of the facility will be the superconducting linear here, which is at this point as 400 kilowatts for uranium, but this is, one hopes that this will be extended to 800 or even 1,000, okay? And then you have various areas. This is where rare isotope production and harvesting will be done. Harvesting will be for possible societal applications, and there will be a reacceleration of some of those exotic nuclei for further experimentation. Okay, this is an ion source. Okay, so this is coming. The first beams will perhaps be delivered in 2021. What will be the reach of FRIB facility? Okay, so this diagram shows the number of isotopes of a given element. This is what the dark one, the black navy blue, shows the current situation. So this is where we are today, known isotopes. So this is the present state of knowledge. FRIB will produce all isotopes here in green. So it will easily double the current state of knowledge. And the blue line shows those theoretical calculations of nuclear landscape, which I showed you earlier, with the drip lines. So this is where this is what theory tells us today. And this diagram tells that the drip line will be reached in several areas on the neutron-rich side. So many new isotopes will be produced. It will access 80% of all isotopes predicted to exist below uranium. Okay? So this is a very awesome reach. No other facility will take us that far. Okay? One example about our process. So the process which will produce gold, in your jewelry. So this is the range of FRIB. So this is this line, and this is where our process is supposed to be. So it will take us either to or beyond this line of expected R process pathway here, okay, or very close. So the extrapolation which will be needed for nuclear theory won't be as dramatic as it is today. So sometimes astrophysicists call FRIB our process machine. Okay, so let me say a few words about high-performance computing, because this is very close to my heart. So today, supercomputing, together with experiment and analytic theory, forms the third leg of the field of nuclear physics. Okay. So theories are a team together with computer scientists and applied mathematicians to make modern calculations which explain new challenging data. Okay? So James Vary, who was here 2 weeks ago, he gave you some nice overview of calculations. So let me just show a few examples which he perhaps did not show. Okay? So this shows year in which a nucleus with given mass was computed precisely ab initio. So as a body problem, using the best known forces, okay? as you can see that in the mid-80s, we're able to go to 3 and 4 body systems. And then in 2000, we had this unusual calculation by coupled cluster method for oxygen-16. But then it took a long time, actually, to go heavier. But today, you can see this dramatic growth or rise, which is almost exponential, and we can calculate elements like calcium-48 precisely. Why is it so? Why this scaling was linear here and is exponential? Because our algorithms to calculate nuclei were not scaling very well. So they were exponential in terms of particle number. And today we have methods which make it possible to compute the nucleus which scale polynomially, okay, like n cubed, when n is the number of particles. So we can beat Moore's law, and we can take full advantage of high-performance platform, okay? So this is where we are today. We can calculate the lightest nuclei using ab initio methods. The medium mass systems we can compute using configuration interaction approaches, well known from atomic physics and quantum chemistry and condensed matter physics, and then density functional theory is the rest. And we are now looking for the overlaps between all those approaches, okay? And of course, now depending of your questions, you will get the nucleus, you know, in different resolutions. If you would like to, if you are just interested whether the nucleus is spherical or deformed, okay, and what is the role of neutron excess, you can take a very simple model and you'll get your answers. But if you want to spend more time and cycles, okay, then you can improve your model and you can get nucleus in a better resolution, okay? And this is what is meant by this arrow dimension of the problem and resolution, okay? So, so here you have very quickly examples of modern calculations. So this is the structure of the Hoyle state calculated ab initio. So in those calculations based on lattice effective field theory, we see the Hoyle state, fundamentally important state for our life, right? Having this 3 alpha cluster structure, okay? Here you have calculations of carbon-12 charge densities in quantum Monte Carlo. Here is this paper which I mentioned, in which we managed to get the weak charge distribution radius of calcium-48. So it showed actually, it showed the neutron matter radius and charge radius, weak interaction radius, and we made predictions actually about the size of neutron star based on this. This is for nuclear fission. So using advanced density functional theory and multi-dimensional configuration spaces and Titan computer at Oak Ridge, we were basically able to do imaginary time propagation from the ground state of plutonium-240 to the outer turning point, and then all the way to fission, and this made it possible for us to predict fission yields. So it's not just like nuclei, okay? We can calculate neutron stars, we can calculate fission of complex nuclei. Okay, so the modern nuclear structure of physics of nuclei actually is truly interdisciplinary field, okay? It connects to QCD and to the standard model. It connects through fundamental interactions to particle physics and cosmology. There are many, many connections which I did not have time to discuss to complex systems which exhibit emergent phenomena. There are many collective phases in atomic nuclei, and there are connections to astronomy and astrophysics, cosmology, etc. So, because nuclei are very present in the cosmos. Okay? So, somebody asked me how many nuclei can you measure and calculate. The point is not to measure all those remaining 4,000 nuclei. That would be stupid, right? We are interested in measuring and inspecting the interesting one. So we coined the term designer nuclei. So designer nuclei, this is what we are doing today. So what we do first, there's a concept. We look what nucleus can be of interest. For instance, radium-225. It has this pear-like shape. in the laboratory system. So there is a chance for enhanced shift moment. Then we make a prediction for the shift moment of radium. And then we develop technology to produce radium-225 in copious amount. So this is where the field is going. We would like to look for selected most important species, okay, in nuclei, rare isotopes, which carry the most exciting, most important information, okay? So that's a message. So I mentioned a long-range plan, 2015, a very, very interesting report. The FRIB facility was put as recommendation 1 to finish it in a timely manner and start the physics program at FRIB, okay? So the outlook, well, the study of atomic nuclei makes a connection between fundamental building blocks of matter, complex systems, and the cosmos. I believe it's an extremely cool field, okay? It deals with fundamental and complex. It is very interdisciplinary. It's very relevant. I did not have chance to talk about numerous societal applications brought by rare isotopes. For this, I suggest you bring Georg Bollen from MSU. He can give you fantastic colloquium on this topic. And we had actually found, there's actually great progress both in experiment and theory. Who could have predicted it 20 years ago, okay? And thank you very much for your patience.
Thank you. So now we have some time for questions or comments.
You seemed a bit pessimistic about reaching the island of super heavies nuclei that you're currently projecting.
No, I'm trying to be realistic. Pessimism comes from realism.
I think you answered my question.
No, it's an excellent question. How can you get there? We need to pump more neutrons to get closer, right? And where are those neutrons? You have to use either neutron-rich targets or neutron-rich beams, okay? But then you need to produce neutron-rich beams of the right nuclei. So they will live for a long time, and they are heavy enough. And this is the major technological problem. So one never says never in this field, but it will take a long time to make significant progress in going towards...
How far towards it can we get?
You see, now I can...
You showed a fairly large gap, and with effort, can we get... Presumably we can start moving a little bit closer to it.
So let me quickly skip this. So this will give us all good perspective. Oh no, let me just go to this, and I will do it in a very simple way. Yep. So super heavies are here. Okay, so this is the current situation. All right. So this is where we are here. Okay, this is element 118, neutron number 176. Using the hot fusion reactions, which turn out to be successful, and calcium-48 beam, if you get more transfermium targets, okay, you will be moving in this direction, okay, here. So you will perhaps make New York Times headlines because you will produce new elements, but you are not going to get closer here. You will be bypassing the predicted islands. So the point is to go to nuclei with Z 113, 112. 112 is copernicium, by the way, okay? So like here, and to move in this direction. And this is where the target beam combination is killing us.
Could you explain more how the rare isotope beam facility works in terms of how many ions, how the ions are produced, what ions are accelerated, is there a target?
Oh, technical details. I have several slides here which might be illuminating, but perhaps we can go through them after the seminar. Yeah.
I'm just trying to understand how broad.
Oh, this is going to be a standard superconducting linear, okay, which will produce primary beam. And then there will be two kinds of reactions which will be used. There will be fragmentation reactions, using this high energy beam, and you will produce rare isotopes by means of fragmentation. So you will put, so your beam, say medium mass beam on uranium target, bang, and you get 50% of nuclear landscape in this reaction. And the whole trick will be now to separate. So separators are very important here. Okay. Another technique is called isol technique. So another technique will be actually here at FRIB in the first stage. This is not going to happen. But what will happen is that some of those fast-moving fragments will be deaccelerated in gas stopper, and then they will be separated, and then will be reaccelerated in another accelerator, which is cyclotron. So this is one of the existing cyclotrons. So there will be two ways of getting into radioactive nuclei. Is it satisfactory?
So I had asked where are they, and what I was referring to was stable super heavies have been for about 50 years or something, and so is the theory. In the meantime, at least 20 years ago, limits on quarks were at the level of 10⁻²⁴ per nucleon, if I remember. Someone had poured a mole of matter through a spectrometer, and they see no quarks. Now, is there an update on that? Is there a limit from experiments of the number of super heavies? Is it an order 10⁻²⁴? And if that number is that small, what makes us think that this is realistic?
Well, I'm sorry. So what do you mean by 10 to the 24?
10 to the -24 abundance of quarks in ordinary matter. There's less than 1 quark per mole.
Oh.
So they're really rare. So, and this came because people poured a huge amount of ordinary matter through some kind of a fast spectrometer. They didn't see one. Right. So the limits on quarks were pursued up to a certain point in time to advance.
Yeah, I understand that you are giving an example of quarks, as an analogy.
Well, then, is there a corresponding search, broad-based search for super heavy nuclei? What are the limits? There must be a search.
Okay, look. So there are two ways, right? There are two ways. The one is to use heavy ion reactions to synthesize super heavy elements, okay? And then, of course, you have this super heavy system. You need to ID it properly, identify it through decays. And this is another discussion.
I'm just talking about ordinary dirt.
Yeah, I'm coming. Second way to search in the ordinary dirt. For instance, in some matter which falls down on Earth from cosmos, to see maybe it was created, because in this astrophysical R process, which I discuss, perhaps if this process happens in neutron star, black hole merger will be going very close to the neutron drip line, and the matter can be moved all the way to super heavy elements. And maybe there are very long-lived super heavies, which exist and came to us, from cosmos.
One of those things blew up.
Yes. So there are many searches of this kind, okay? Many, using mass spectrometry.
So now there's a limit on that, and that limit gives you the extra experimental handle, which has to confront this whole theory.
Yeah, but the problem is, yes, I'm sorry, I just want to address this very interesting question. The theory, unfortunately, at this point, can tell you very little, okay? This is the slide which I did not have chance to show, okay? As you go to elements which are heavier, okay, theory predicts that nuclear matter in those nuclei, super heavy and hyper heavy nuclei, will have all these incredibly complex topologies. We have so many protons there that they will try to repel each other, so protons will go to surface, thus creating voids and bubbles, bubble-like structures. So these are the actual predictions from various calculations. Now, there is no single model which, based on realistic interaction, can now go through all those phases of nuclear matter in super heavy elements, and in addition to it, to calculate their stability. You would like to calculate, make predictions for spontaneous fission of a bubble-like nucleus. This has not been done yet. So I simply don't know what can theory tell us about this upper right corner. We just don't have calculations with exascale computers. This perhaps will be done. This scan needs to be done.
Yeah, I mean, this work that you have done on the fission fragments,
Yeah.
that could give
This will be extremely useful,
because,
yes.
Yeah, you see how
Yes.
they can populate.
Absolutely.
Yeah.
But, you know, I mean, to look at fission of nuclei like this, which has nothing inside and everything is around the surface, will be one hell of work.
Okay, so thank you very much.
Thank you very much.